Hi, everyone. Today we're on Unit 10, Lesson 4. It should be Lesson 4, Limits at Infinity. Before we begin, let's go back to kind of the last couple of days. And in our do now, wow, a lot of typos. In our do now, we're going to evaluate each limit. So to evaluate the limit as x approaches 3 of 2x plus 8, remember, we just plug in 3 for x and evaluate the function. In part B, the limit as x approaches 2 of x squared minus 4 over x minus 2. Remember, always start out by plugging in. That's the first place we start. And I get 0 over 0. When I get a 0 in the denominator on my first try, it's undefined, but that doesn't necessarily mean I don't have a limit. So I'm going to go back to the function, factor it, simplify, and evaluate in our simplified version. And now I do get an answer. In part C, start by plugging in. You always start in the same place. Negative 4 over 0, we're undefined. I'm going to go back to my original function, factor, simplify, and reevaluate. And this time, since I don't get an answer on my second try, the limit does not exist. Okay. So up until this point, we have been analyzing the limit as x approaches c of f of x, meaning as x approaches some number c, what is happening to the graph of my function. Okay. And over the past couple of days, we've been describing those different situations. Okay. If you plug in a number and you get the answer, that's your limit right away. Sometimes we won't get an answer, but that doesn't necessarily mean that we don't get a limit. And sometimes we don't get an answer and we don't get a limit. And we talked about what these things, the different things that these mean. Remember, this would be a hole in my graph. And this would be an asymptote. You don't necessarily have to write that unless you're asked. Okay, so just be aware of what the question is asking you. In this lesson, we're going to analyze limits at infinity, meaning we want to know what's happening to my graph as x goes to infinity or x goes to negative infinity. What's going on with the graph of the function? When we do this, it's similar to analyzing end behavior. And remember, that's just what is happening to the y values of a function as we plug in really big or small x values. Okay, so we're talking about the end behavior. Now, in this course, we studied the end behavior of our functions already, in our polynomial function, in our rational function. So we're going to kind of combine this now with limits. So the limit as x goes to infinity of x cubed. So I just want to kind of just think about the graph. Can you picture this graph in your head? Okay, so in these examples, we're just going to think about it. What is x cubed? X cubed is our kind of snaky guy, right? If we were to plug this in our calculator, that's our x cubed function. And as x goes to infinity, what's happening to my y values? They're also going to infinity. So contrary to what we said in the beginning of the unit, okay, we can use positive or negative infinity to describe limits. When we analyze the limit as x approaches c, it has to be a number. But when we analyze the limits as x goes to infinity, we're describing the behavior, so we can actually use positive or negative infinity. Let's just add a little question here. What if I asked the limit as x goes to negative infinity of x cubed? If you kind of visualize the picture, as x goes to negative infinity, my y values are also going to negative infinity. The limit as x goes to infinity of 1 over x cubed. So now use common sense. What is happening to the graph? If I plug in, if I'm doing 1 divided by like 1 cubed, that's 1. 1 divided by 10 cubed, that's 1 over 1,000. My number is going to get smaller and smaller and smaller and get closer to 0. So technically we're dividing by, right, a bigger number. And when we divide by a bigger number, our answers get close to 0. And if you can't see it, just plug it in your calculator for right now. And we're going to talk about the rules in a second. But if you look at the graph, as x goes to infinity, the y values are getting closer to 0. The limit as x goes to infinity of 2x cubed over x cubed. Well, no matter what number you plug in, what's happening? When I plug values into this, and I'm putting, like, let's say I put 100 in, 100 cubed over 100 cubed, doesn't matter what it is, it's going to cancel out, and my answers are all going to settle at 2. Okay. So basically, when we evaluate limits, as x goes to infinity or negative infinity, we want to think about the function we're dealing with. If your function is a polynomial function, we're going to use the end behavior rules for polynomials, meaning doesn't matter how many terms the function has, you always take the term with the highest degree and the lead coefficient. And if it's even degree and positive, our answers, our end behavior is up, up. Even degree and negative, well, based on transformations, that's going to flip our graph down, down. Odd degree and positive, that's when we get this guy here. Odd degree and negative, we're just going to flip that guy. And if that doesn't work, just use common sense. You're going to think about what's happening in the graph. And I will explain that in just a moment. For rational functions, we're going to use the same rules that we did for horizontal asymptotes. So when I have a rational function, I want to compare the terms with the highest power. N is the highest power in the numerator. D is the highest power in the denominator. If N equals D, we take a ratio of the coefficients. Example 3. The powers are the same, so no matter what, it's just going to cancel and you're left with whatever number. If n is less than d, the limit is 0. The power in the numerator, right? This is really x to the 0 up top, it doesn't really matter. If you think about it like this, if you're dividing by a bigger number in the denominator, your answer always goes to 0. Same. I call this bottom heavy. If n is greater than d, our answers go to positive or negative infinity. And technically that would sort of be this example here. Even though it doesn't look like a rational function, this is really x cubed over 1. But we don't have to worry about that so much. We call this top heavy. For these, we're going to do some thinking. These are examples of a slant asymptote. And we're going to think about what happens if I plug in a really big positive or a really small negative. Okay, so just at this point, we're going to do some thinking. So now let's work through the examples because you're going to see how easy this is to do. The limit as x goes to infinity of x to the 6 minus blah, blah. It does not matter what the rest of the terms are. You only care about the term with the highest power. X to the 6th. Since it's a polynomial function, this is the only term that matters. Even power, positive lead coefficient, right? It's positive 1 out front. Even in positive, my graph is up. So as I plug in as numbers as x goes to infinity, or even if you think about it this way, if you raise a positive number to an even power, your graph is going to positive infinity. In example 2. Again, look at your function, it's a polynomial. So you only care about the highest power. Take that term out and now analyze it. It's a cubic, so it's an odd power and negative. As x goes to infinity, sorry, negative infinity, odd power negative, my answers are going to positive infinity. Here's the thing. If you don't want to memorize the rules, here's where I say do some thinking. I'm evaluating negative infinity, so I want to know what's happening when I plug in some type of negative number. Negative cubed is negative, negative times a negative is positive. My answers are going to positive infinity. That's how easy this is. The limit as x goes to infinity of x squared plus 2 over x cubed minus 1. The term with the highest power in the numerator, the term with the highest power in the denominator. Take those out and analyze. My bottom power is higher. This is bottom heavy. Answers go to 0. I'm dividing by a bigger number, so my answers are getting smaller. Highest power in the numerator, highest power in the denominator. Same power, they're going to cancel each other out. So no matter what I plug in, my answers are getting closer to negative 2/3. And if you remember from our rational function, we're never going to hit it. It just means the graph is getting closer to negative 2/3. the limit as x goes to positive infinity, 9x squared over x. Top heavy means think. So I'm going to positive infinity. So I want to know what's happening when I plug in a positive value. So that's going to be a positive number in the numerator, a positive number in the denominator, positive over positive, I'm going to positive infinity. The limit as x goes to negative infinity, highest power, the term with the highest power in the denominator. Bottom heavy, right? So it doesn't matter whether I'm going to positive or negative infinity, my answers is going to be 0 because I'm dividing by a bigger number in the denominator. The limit as x goes to negative infinity of x cubed minus 8 over 2x squared. Top heavy, so I have to think. So what's going to happen as I plug in a negative number? I'm going to have a negative in the numerator. When I square a negative, I get a positive value, so this denominator will be positive. Negative over a positive, my answers are going to negative infinity. In example 8, the term with the highest power in the numerator, the term with the highest power in the denominator. Since my powers are the same, right, that these are both 1, they're going to cancel each other out. 2 over negative 1 is just negative 2. Okay. So we're not going to worry about the factoring or any of that when we're dealing with the limit as x goes to infinity. That's end behavior. So we're thinking about what's happening as I plug in really big or really small values. Now let's just for a moment switch gears. Think about what would happen with what we call our transcendental functions. These are our e's, our ln's, our trig. Now basically with these, we also kind of consider our rules, but okay, we need to memorize our parent functions. And we need to utilize some transformation rules. So for instance, the limit as x goes to infinity of e to the x, any exponential function you guys should all have memorized just kind of goes, right? Our exponentials are these. So as x goes to infinity, the graph of the function is going to infinity. Well, e to the negative x, what are we doing? We're flipping that graph. We're flipping it over the y-axis. You don't have to draw it, but you should be able to visualize it. And in this case, as x goes to infinity, our y values are going to 0. Approaching 0, they're never going to reach it. The limit as x goes to infinity of cosine x. Well, our cosine function just goes like this, right? In either direction, on and on and on and on. It doesn't ever settle at a number. It doesn't ever go to infinity or negative infinity. So this limit does not exist. Little weird, you really don't get that type of question. Here's something that may show up in your calc course. We're going to talk about it. It's not going to be a part of this test, but just think what's happening. Limit as x goes to infinity of e to the x. Well, if we think about what's happening in the numerator, our y values are going to positive infinity. If we think about what's happening in the denominator, our y values are going to 0. Remember, they're approaching 0. So this doesn't mean we're undefined. It just means I have a bigger number and I'm dividing by a smaller number. So the top is growing at a faster rate. So my overall answers are going to positive infinity. This is just what I wanted to talk about. Don't worry if it doesn't mean anything. It will make more sense next year. Okay? The main focus of this lesson is going to be on the algebraic, the polynomials, and the rationals. Okay, so I'd like you to practice some questions for homework. I just want to point out that number 10 is a difficult one on your homework question. So you might want to just cross off number 10 and not worry about it. Okay, guys, thank you. Have a great day.